First
Yeah,
of all,
yeah, it is coming.
I would like to thank the organizers for giving me this opportunity to present in front of you, and also Dr. Somkumar Sharma for chairing this session. And now I'll be talking for the next half an hour or so. The achievements we made for from the LiDAR observations from the Gadanki, more than 2 decades of observations are available, almost like 22 years of observations are continuously observations are available. And what we achieved from these observations, since the students are sitting here, I suggest you may be from different backgrounds and you may not be following up my presentation, but you please take a message that there are ample of opportunities available in this field of research, right from the development to the retrieval algorithms to the signal processing to the application. So if I tell more, I don't think any of you may be following, but this being the workshop for the experts, so I should make sure that some of the results should be shown for the other people also. So kindly bear with me. So myself Venkat Ratnam from National Atmospheric Research Laboratory. Before I should, if I talk my presentation, I should remember a pioneer of middle atmosphere research in general and LiDAR research in particular, Professor B.V. Krishnamurthy, where we had an association of more than 3 decades. And he is the almost like a father of LiDAR technology in India, we can say. He has done a lot of research in the LiDAR development and also the application. Recently, he passed away in April 20. So I will be in the next half an hour. So I'll be covering what are the remote sensing techniques. Of course, this is being the LiDAR, but in which way this LiDAR is different from the radar, I'll be telling in the one slide. And then why this LiDAR has been introduced at Gadanki, that I will tell for the next couple of slides. And what we did it in the using this Rayleigh-Mie Lidar observations in the last 2 decades, covering the temperatures in between 30 to 80 kilometer and clouds 8 to 20 kilometer and aerosol 8 to 30 kilometer. You might be noticed that I am talking about a little higher altitude covering the middle atmosphere, and all complete yesterday studies and other studies will be covering the tropospheric process. But this LiDAR has a unique sense that it can cover the complete middle atmosphere. By combining both the Mie and Rayleigh, we can almost cover right from 10 kilometers to the 100 kilometers. And then finally, I will summarize and the way forward. So several speakers has told why this LiDAR is being used and how they are used. But this slide summarizes means in which way these LiDARs are different. And if you see, we will be using electromagnetic radiations, the spectrum, to sense the atmospheric process. So the atmosphere has the property of scattering or absorption or reflection. So any process what we are interested to deal, so that depends upon our interest, and suitably we have to select the band. Suppose if you want to see the clear air motions like winds, waves, turbulence in the atmosphere, we need to go to this kind of radars. It starts from HF frequencies to the L band, almost 1.3 gigahertz. So if you from this, see the wavelength should match, then only we'll get the backscatter or reflection or the absorption will happen. So from this kind of radar, we'll be seeing the clear air motions, convection, and to some extent the precipitation and rainfall. Suppose if you want to study the clouds and precipitation, we need to go a little bit higher frequencies like S band, C band, KU, and this band. So now, if you want to, but these are all, we will not get any information related to the aerosols, and to some extent the subvisible clouds we cannot get from these kind of radars, and also the trace gases. Most important, the information from the trace gases we will not get from these kind of radars. And of course, yesterday there is a talk from Russian. He was mentioning that how the temperature and water vapor can be retrieved from this kind of LiDAR. So this is the difference, how the radars and LiDARs both will complement. Suppose if you have any station with both radars and LiDARs are co-located, you see what is the advantage. I'll be telling in the couple of slides next. So at Gadanki, I don't know how many of you know, near Tirupati, from 40 kilometers from Tirupati, we have established the second biggest radar in the world. And it is being operated since 1991, almost like 3 decades now. And this will be covering, I'm showing the range time intensity map of the backscattered signal to noise ratio. This is from morning 9 to evening 3 o'clock. You can see this from 3 kilometers to almost like 100 kilometers. So you'll be getting very good information up to like 21 kilometers from the radar. And also again, it starts from 65 to 80, 85 kilometers. We'll get very nice information, continuous information. Every 1 minute we'll get all the information from this kind of radar. But there is a big gap. This radar cannot see. It's a blank. there is no atmospheric process where this radar can see that is happening between 20 kilometers, almost like 60, 65 kilometers. So to fill this gap, with the collaboration of Communication Research Laboratory of Japan, we have established this LiDAR. It is difficult to see. This is a very green color light, right from the distance almost reached to 100 kilometers. We established that. Then that we could able to cover this very, very nicely this region. Of course, whatever the radar was not giving is not possible to get, but some information we'll get simultaneously right from surface to the almost like 100 kilometers by combining these two different instruments. So from the radar, as I mentioned, we'll get the turbulence, winds, waves, and other properties. But from the LiDAR, we'll get aerosol cirrus clouds and temperature profile. And this we established in 1998. Since then, this is the LiDAR and both radar has been extensively used in several campaigns. And to name, you can see these are all very extensive campaigns. In fact, it's first of its kind, not only in India but across the world. So this combined measurements has been used first in the equatorial wave campaign started in 1999 and 2000, where continuously more than 40 days continuous observations we made with both radar and LiDAR observations. And I'll be showing one of each of these results in the coming slides. Then Middle Atmosphere Dynamic Program, MIDAS, where we have launched the rocket sondes from Terrell's Tumba. Then we have simultaneously operated this LiDAR at Gadanki, almost like 500 kilometers away, but still the process will be remain same. I will show in the my next slide. Then we have extensively used this LiDAR for the solar eclipse campaign conducted in 2010 and 2019. And also we have used these instruments for the vertical coupling process, which named as a study of atmospheric force and responses. We conducted for 5 years. Then these instruments are also used in process 1 and phase 1 and phase 2. And more important, the tropical dynamics campaigns, we have extensively used this LiDAR system. And it's also used in pre-monsoon campaigns and ISRO-NASA battle campaigns. I'll be touching upon what is importance of this battle. And also my colleague Dr. Ravikiran will be talking more on the balloon-borne aerosol cloud interaction studies in the next talk. And also yesterday, Dr. Jairam sir was mentioning that the Pinatubo volcanic eruption, how it has kept the sulfate aerosols in the stratosphere. So I'll be telling about the recent volcanic eruption. It happened in 2016. And then we also participated in ISRO French Stratral 2 campaign. I will be telling just brief details about that one. Now, this is the first one, a typical structure, what we will receive from this LiDAR information. So this is the temperature profile, right from surface to 100 kilometers. You see, many of you may not be knowing that temperature goes on decreasing with respect to altitude up to some extent, but after that it starts increasing again up to 50 kilometers, then again it decreases up to 100 kilometers. The reasons behind are well known, but I will not tell much here. But what we get from this LiDAR is from this utility, almost like 8 to 30 kilometers, we will get the aerosol information and also the cirrus cloud. And also from 30 kilometers to almost like 80-90 kilometers, we will get the temperature profile. So with this thing, what we did is, from the Rayleigh LiDAR, it covers from 30 to 80 kilometers. We used, extensively used for to characterize the measures temperature inversions, semi-oscillations, and tropical stratopause various. Stratopause is this much. And using my LiDAR, we have studied the cirrus properties and also vertical distribution of aerosols. And since because we have used more than 2 decades of observations are there, we have also used these observations for the climate change studies. And it includes both the middle atmosphere temperature, cirrus properties, and utilized aerosol. And more important is that from yesterday, the several speakers have might have told, why, see, there are several instruments that are coming up. Every day I can say 1 or 2 instruments will be being added for probing the atmosphere. But these instruments has to be validated. And this LiDAR system has been extensively used to validate many of these different instruments. Not only the instruments, even the models also being validated here. To mention a few, the first I will start with the validation. And we have used this LiDAR system to validate the very high, low density temperature and winds. So generally that balloons will be giving, you might have seen that IMD will be launching balloons every twice in a day, and they will be getting meteorological parameters like temperature, relative humidity, water, winds, zonal and radial winds. But we do not know at low densities if you go beyond 30 kilometers whether they are reliable or not. To test that, we have used the high altitude balloon, and we simultaneously launched when we are operating the LiDAR, and we could able to test that 30 to 45 kilometer winds has been verified, and including temperatures has been verified with this LiDAR. Then, as I mentioned, the rockets foundations were being launched from Terrell's Tumba, and between 2002 to 2005, where we operated simultaneously this LiDAR. Next slide, I will be showing that slide, that result. And several satellites has been introduced. Even just my previous speaker also told that winds from the spaceborne lidar, that is Aeros, and such kind of instruments has to be validated. In fact, my previous complete study is only on validation. So these our lidar also is used in several validations like HR. These are all NASA satellites launched from 1991 to the recent last 1 year. So we use the comparing the 30 to 80 kilometer temperatures and utilize aerosol, particularly the Calliope and also cirrus from the Calliope. Then we also validated the ERA5 and MERA2 some of the products using these lidar observations. Now, as a typical example I'm showing here, you can see these are the Rayleigh lidar observations for average between 98 to 2007. From 30 kilometer to 80 kilometer, you see the monthly variation. And these are from the rocket sondes from Tumba. You can see the more or less similar variations. Exactly it is replicating both rocket and Rayleigh lidar. But if you see the heights of the stratopath, this peak maximum temperatures near the stratopath is able to pick up nicely, but they are unable to give the exact magnitude of the temperature. You see there is underestimation of these rocket sonde when compared to the lidar. So such things has to be known very clearly before we use any data for understanding the physical process of the atmosphere. And as I mentioned, that radar has been used extensively for understanding the mesospheric processes. And this is a typical example where we will get a continuous echoes almost like 70 to 75 kilometers using the radar. And we have more than 2 decades of data is available, and we are used to study the seasonal variation and why this is confined to only 70 to 80 kilometers and why not at other altitudes. Then we are surprised. Then we thought that at the Japan latitudes, they used the similar radar, and they could able to see that at the mesopass, where I showed that coldest temperatures, that is there they are getting such kind of echoes. But to our latitude, if you see the mesopass, that coldest temperatures in the Earth's atmosphere, it is not at 60 to 70 to 75. Rather than it is almost like close to 100 kilometers. So we are supposed to get these kind of echoes at 100 kilometers, but we are not getting those echoes, but instead we are getting 70 to 75. Then we are surprised from what is the process behind this. Then fortunately, as I mentioned, that LiDAR was established in 1998. These are the first profiles in the 1998, I think 18 March 1998. These are first profiles. There we could see there is a temperature inversion has there. As I mentioned, in fact, temperature goes on decrease from 50 kilometers to 100 kilometers. But suddenly there is an increase in temperature, and that at the same altitude is coinciding with the MS radar echoes. So we could able to explain that these echoes are because of the temperature inversion. And what happens at temperature inversion? Any wave going from the lower atmosphere to the upper atmosphere, when temperature inversion is there, it try to break, and that breaking will generate the turbulence, and that turbulence is the background condition for it to satisfy the radar to get these kind of echoes. So we have extensively because we have a lot of data. Then we try to compare how the satellites are looking. See, one disadvantage in my previous slide, if you see, this is the statistics, number of days we used in each month. You can see in the monsoon season, because of cloudy conditions, we cannot operate this lidar. These are the clearer lidars. So if you see the rocket that doesn't have that kind of information, that kind of problem. And the same with the lidar, with the rocket, because rocket is looking from the top. So the clouds will not be perturbing. So we will be getting very less data set in the monsoon season from the lidar, but the satellite doesn't have that kind of problem. So when we compare it is matching very well between the satellite and these our lidar observations, giving confidence that these are real temperature inversions. Then we obtained the similar like radar, we have obtained the statistics. Then we could see it is able to have the two is a wavy type. So it is picking up in the equinoxes in the March, April, and also in the September, October. Then we combined both. Then we could see that this radar, where we got this maximum signal to noise ratio, echo occurrence and strength, at the same time when we have the temperature inversion. So we could able to get the fundamental understanding of the mesospheric dynamics by combining these two independent measurements. Then this lidar has been now. First of all, why we are observing every day we are monitoring the atmosphere, because we want the model atmosphere. For the model atmosphere means we have to predict the atmosphere. For that we need to the model atmosphere. So what we did is in the last 2 decades of observations, we collected from several sources, including the lidar, particularly for getting the temperature right from surface to the 100 kilometer. We use the radio sonde from 0 to 30 kilometers, and 30 to 80 kilometers we use the Rayleigh Lidar observations. Then 80 to 100 we use the Sabre satellite observations. You can see there is it is produced very well that low temperatures here, and also maximum temperature in the stratopause and minimum temperatures again in the mesopause region. So this kind of model information is very, very important. Particularly now ISRO is looking for the re-entry of the vehicles. Manned space shuttle is going very soon. So for that, if you want a re-entry, once the re-entry, that because of the rupture, there will be heat will be generated and fire will be generated. So how much background wind is able to get to understand those processes, this is very important, and this model has been used for the ISRO manned mission. Now, again, as I mentioned, now because we are covering right from surface to 100 kilometers by combining these two information. So if any cyclone or convection is happening somewhere in the Bay of Bengal or Arabian or Indian Ocean, what they will do, they will generate different types of waves. And these waves will be propagating horizontally and vertically. So we have to understand these processes also. Then what we did during the process of one of the cyclone or convection, we operated the radar and lidar simultaneously. And you can see this 0 to 21 kilometers we operate the radar, and again 65 to 85 we have radar, but in the middle we have used the Rayleigh Lidar observations, and this is a typical altitude 18 kilometers, 45, 60 and 73.2. When we could see that this kind of waves has been generated right from surface, and again it has gone to the middle atmosphere. So such a nice vertical coupling studies we can make by combining these two different instruments. Then we have used this momentum flux. Means the amount of energy being deposited in the background atmosphere, that we call as a momentum flux. And this momentum flux has to be estimated properly to understand the background atmospheric dynamics. And by combining both, again, the radar and lidar, we have estimated the momentum flux using these equations. Don't worry, these are very complicated equations. But what I want to say is, in the overlap region where the radar and lidar is having, you can see very nice that calculations, though different instruments, different parameter. This is MS radar is giving the vertical zonal meridional and vertical wind, whereas radar lidar is giving the temperature. Though different techniques, different calculations, but you can see that overlapping region is exactly matching. Such a beautiful information we'll get by combining these two information. Then coming to the next part of my talk, and this is the slide, I think background, this is the logo of this workshop. Dr.M might have selected this data, and this we have obtained from 25th May 2015 in one of the pre-monsoon campaign, where you can see right from 6 kilometer to 20 kilometer, there is a thick cirrus, it's a downward propagation of thick cirrus. You can notice right from 14 kilometers it has reached to 10 kilometers or 8 kilometers sometime, and this kind of beautiful cirrus cloud properties we can get it from this lidar. And at the same time, when we operated the radar, we could see that there is a downward wind. Exactly, this is the time where we are taking the radar snapshot, and you can see there is a clear downward wind, and this downward wind is making these cirrus to bring down. So such kind of information is very, very important in understanding the background atmospheric process. And then we have used the same lidar system for the understanding the aerosol. Yesterday, several speakers were mentioning that how the aerosols will be retrieved and what is the importance of aerosol. And this is not the Rayleigh-Mie Lidar, but this is from the boundary lidar. This is a different type of lidar, but again, this will give right from surface to almost like 8 kilometers, where we could see this is the boundary altitude. Boundary altitude is very sensitive to the surface properties. And at Gadanki, this is the boundary altitude if you see from the month to month. And this is the aerosol what we get a profile. During the monsoon season, we could see the very thick aerosols is sitting just above the boundary altitude and very clean atmosphere below. And whereas the aerosols are restricted to within the boundary layer during the other months, then we could not understand what is the reason why that monsoon season there are no aerosols below the boundary altitude. Then we could able to tell the process using the dynamical aspects. During this season, we used to see that the low-level jet, this is a part of monsoon circulation. Low-level jet is at 1.5 to 2 kilometers. A jet will be propagating from the Arabian Sea towards India, and those are bringing a lot of aerosols. And at a given time, if you see anywhere in the southern part of India, you will get this kind of layer. At the same time, you see that relative humidity is very high during the monsoon season, and this relative humidity might be acting that the hygroscopic growth of the aerosol, And that is another reason for getting this kind of enhanced aerosol layers. Then what is the reason why there is no aerosol here? So then we could take the rain. That rain will be used, the aerosols will be used as scavenging, wet or moist scavenging, and those are being removed below the cloud, from the cloud. So that's why we could see there is a clean atmosphere in the monsoon season, whereas in the higher altitude there is a elevated aerosol layer sitting there. And of course, background dynamics also plays an important role. I'm not explaining more details here. Then why it is not restricted only here and why not it is going up? Then using again the dynamical aspect, that wind shear is the two winds, one is going towards west and one is going towards east. So in this process, what is happened, anything process happening here, they will not allow to penetrate to higher altitude. So this is exactly what is happening. During this season, monsoon season, we could see that the large wind shears in the vertical shears in the horizontal wing. So that is making not to allow this one. But to our surprise, when we operated the Mie Lidar, we could see that there is again elevated aerosol layer sitting only during this season. When we tell that why, when this aerosol layer is not able to penetrate higher altitudes, from where this has come. So luckily we have satellite observations in the inaugural talk by Jean Paul. He was mentioning about aerosol, Asian tropopause aerosol layer, where this is the what yesterday he was showing. So this is in India, and during this season, what is happens, almost like 30 degree to 120 degree east, there is a thick aerosol layer will be sitting between 16 to 18 kilometer, and at Gadanki, our region is here, and that is we are seeing as a part of that big Asian tropopause aerosol layer. And this aerosol layer is very big, it's having a lot of regional and global impact. To understand this, in collaboration with NASA, we have made an agreement to investigate this, and we have launched several high altitude balloons from Hyderabad, Varanasi and Gadanki to understand these aerosol properties. And our LiDAR was is working as a backbone for this understanding this atoll also. Then we also use this LiDAR for aerosol cloud interaction studies, and I'll not touch upon this topic because my next speaker will be talking more only on this topic. And there is another presentation by one of our student, Ms. Renju, will be presenting the first cut observations from this aerosol cloud interaction. Then yesterday that Professor Jayaraman sir was mentioning that when Mount Pinatubo volcanic eruption happened in 1991, luckily the LiDAR could able to detect in 92 to 93 that enhanced aerosol layer in almost like 17 to 20 kilometer. But there is a recent volcanic eruption happened 15 degrees south, this we call Amber eruption, in April and June 2018. In fact, this eruption started, this is our site, and eruption started here. And this is from July, December, and the next year, September. You can see how that, wait one second. Okay, it started here, then started moving first eastward. Then in the no time, within the month of almost like 3 to 4 months, it has spread throughout the globe. So any eruptions happened anywhere in the continent or across the globe, that can penetrate, that can deposit huge amount of sulfate aerosols in the atmosphere. And this is you see within the 3 to 4 months, it has spread throughout the globe. And slowly after a year after that, it start dissipating. But this will give a lot of impact on the background atmosphere, and several processes will be hampered. So then we have operated our LiDAR simultaneously, and you can see these are our LiDAR observations, and these are from the satellite observations. At almost like 18 to 22 kilometers, we can see that enhancement in the aerosol layer from the LiDAR, and where the satellite is able to reproduce those observations. But satellite is the one snapshot, it will go, and all the properties will not get. But the advantage of LiDAR is because it is continuously monitoring, and that process has happened almost like 1 year to 1.5 years. So we could able to get all the properties of this volcanic eruption, how the size, shape has been changed in the course of this time. That kind of details we'll get from these LiDAR observations, where satellite cannot give all those details. And what happens once this aerosol has been deposited in the atmosphere, what will do? It will affect the background temperatures. You can see this is from radio sonde from Gadanki, our observation, 2006 to 2018-19 plotted. You can see when the eruption is there, you can see the lowest temperatures has been recorded. So that has that much background effect that volcanic eruption has on the background atmosphere. So we also use this LiDAR extensively in the Tropical Tropodynamics campaign jointly conducted by Space Physics Laboratory, Vikram Sarabhai Space Center, and NERL. And basically, this LiDAR used to get the properties, cirrus properties, temperatures, and aerosol profiles. We have addressed several aspects, but I will not show any of these results because it will be boring for you. But one thing what we got it, we could able to get this detailed process happening in the Utilus region. You see, this is the cirrus occurrence. From the LiDAR, you could see this is a cirrus occurrence, and this started almost like 11 kilometers and going to up to 18 kilometers with a peak around 16 kilometers. And this is the TTL thickness. And if you see why this, what is happening in this one, the vertical wind always over the Gadanki will be like it will be in upward motion, and the ozone sonde we are used for the ozone minimum. There are several definitions for the tropopause, and one of the basic definition is for the temperature. But we can also get from water vapor or convective outflow level or several definitions. I will not touch upon all these details, but these are this kind of detailed process we could able to get by using the LiDAR observations. And then, as I mentioned, the LiDAR is again our point observation. Gadanki will see, but such LiDARs we cannot install throughout the globe, particularly over the ocean. We cannot get anyway. Yesterday, Dr. Shivakumar was mentioning the network of LiDARs available across the globe. You can see you can count almost like 20 to 30 LiDARs across the globe. So we cannot get complete picture of this kind of cirrus thing from the covering the globe with the surface observations, but the satellite can see. So this, when we see the climatology between 98 to 2013, this is a cirrus, this is a tropopause, convective outflow level, and the maximum, this is called, we call it the TTL thickness, TTL layer, tropical tropopause layer. And this is exactly reproduced by the satellite observations. The Calypso, whenever it is passing over the Gadanki, we could able to see both the statistics are showing very, very similar statistics. So the advantage of satellite is it is looking from the top, and the cirrus, more cirrus we will be seeing in the monsoon season, where that is the disadvantage of LiDAR from the ground based, and that will not give much information because when the cloudy system, when more clouds are there, it cannot give information. So that is the advantage of LiDAR looking from the top. So by combining these two, you can see, you can get that all the details of the cirrus properties, and this cirrus is very, very one of the important parameters for the climate change related aspects. And I will not give details of all these statistics. But what we see is the subvisible cirrus cloud. In one of the slide I mentioning that the logo of this workshop, that the cirrus was downward propagating. So that what will happen, it is an indicator of climate change. We have obtained the subvisible cirrus properties right from 1998 to 2014. You could see that the altitude, it is increasing in altitude. So initially it was at 14 kilometers, now it has reached almost like 15 to 16 kilometers. And this is increasing about 41 meters per year. It's increasing. It's a statistically significant result. So if you operate for more than 2 decades of the observations, you can see the beautiful, the climate change aspects can be recorded in our observations. And at the same time, we have used the Calypso was launched in 2006. Then we have also obtained the similar properties, and both are showing this consistent increasing in the subvisible cirrus cloud. And the several aspects we have investigated. I will not touch upon all those things. Then coming to the, as I said, the global warming climate change, people will be talking to related to the surface. The 1 degree increase in the temperature, 2 degrees temperature increase, people will call the global warming. But this warming is not restricted to the surface. It will have the effect right from surface to almost like 100 kilometers and even beyond. Nowadays, people are talking about the thermosphere shrinking, and it has the effect on satellite drag. So several things is happening not only at surface but throughout the vertical altitudes. If you see, we will be launching the radio sonde every day from 2006, and using this 2006 to 17 when we got the trends. You can see that the tropospheric warming is not restricted to surface, but it goes up to 15 kilometer altitude. And there it started the cooling. And it started cooling, and you can see up to 25 kilometers that cooling is there, but it didn't stop. But after that, radio sonde will not give any information because beyond 30, up to balloon burst altitude only, we'll get the temperature information. But beyond that, using the LiDAR observations, we continued from 30 kilometers to 80 kilometers. You could see that the cooling trend started not only restricted to 30 kilometers, but it started increasing. Means you can see throughout the altitude that the cooling is there, even up to 70 kilometers you could see. So combining different observations, you can see how beautifully we can address the societal problems also, that global warming, climate change. Very nicely we utilized these highly calibrated, high sensitive measurements. We could able to address the issues related to global warming or climate change. Then, of course, I will not touch, I will just keep. So now coming to my ongoing and way forward using these observations. As I mentioned, we have with NASA, we have collaboration with NASA to understand the Asian Tropical aerosol layer, where yesterday Dr. Jean Paul was mentioning. And during 2015 to 20, we have launched 92 high altitude balloons. These balloons will carry almost like 100 kgs of the payload, and they can go, and we can tune that balloon to not to float, not to fly, but we can float it at a desired altitude. This is very challenging, but we could, I think we have the biggest that kind of facility by Tata Institute of Fundamental Research. It is in Hyderabad, and at that facility, we have launched this kind of balloon. So we have tied all the sensors to this balloon, and we've flown, and simultaneously we have operated the Lidar at Gadanki at several places, including Mount Abu. Some of the observations are there, and there are some observations from Nainital. So this to address those issues, we have combined both ground-based and this institute measurements to understand this atoll. Then we have the recently in collaboration with the France, where we are this kind of balloons. These are all like actually after going to some altitude, it will float and we can cut it wherever we want. But the French people, they have launched the super pressure balloons, where they will be launching from the island called Seychelles here. It will be located here. And in the period of like 80 to 90 days, it will complete one rotation across the globe. It will make. So such 8 balloons were launched in November 19 to February 20, and 25 balloons from October 21 to August 22. Now still they are going on, and we have the final this kind of campaign in 24 and 25. And during these passes of this balloon, in fact, those balloons are carrying all the it measures the aerosol, background temperature, and water vapor. Basically, this including the trace gases like ozone, to some extent some nitrous oxide. This kind of sensitive measurements are there. And at the same time, we'll be operating all our instruments at Gadanki, and particularly the aerosol information we are getting from the Lidar information during these kind of campaigns. Of course, we are signed again to have the next phase of campaign, and this time we are combining these campaigns according to the aircraft campaign from the Japan. So Japan, they are launching the aircraft, and it will go almost, it will reach to Bangladesh, to Indian region. At the same time, we'll be operating all our radar, and we'll be having this kind of balloon campaign from Hyderabad to address this Asian Tropical aerosol layer. Then we are also going to use these LiDAR observations to get the temperature from the Meteor radar. In fact, Meteor radar, I do not know how many of you aware of this Meteor radar. Using this Meteor radar, right from 70 kilometers to 110 kilometers, you will get the wind based upon the meteorites entering into the atmosphere. So, but we will not get the wind temperature information from that. Though we will get the temperature information from the LiDAR, but LiDAR is restricted to only night time. Daytime we cannot operate this LiDAR. And to get the 24 hours temperature, by combining these LiDAR observations at a particular altitude, we have to seed if you want to get the temperature, we have to seed first the gradients in the temperature. These gradients in temperature will take from the LiDAR, will seed at that altitude, then we can get it will be independent from the Meteor radar. So by seeding these gradients in temperature from the LiDAR, we can be able to get the temperatures from the Meteor radar 24 hours, 24/7. 24/7 by 365 days, you will get this kind of very high resolution temperatures from these Meteor altitudes. And by combining, as I mentioned, we have the LiDAR and radar, and by combining these two instruments, including the Meteor radar from SU University Tirupati, how we can probe the light from surface to the 110 kilometers round the clock, we can measure all the atmospheric process happening in the atmosphere. So these are our some of the campaigns we already conducted in this kind of by using this kind of synergy in the measurements. So to conclude my thing, so as I mentioned that climate change is not restricted to surface alone, and there are several things happening because of global climate change. The convection is increasing and water vapor is increasing because holding capacity of the water vapor will increase with increasing the temperature, and at the same time that means convection is increasing, then wave activity will increase. This wave activity is also will once increases, it will be part of the background atmosphere once we go from lower to the middle atmosphere. And we also see in the tropopause altitudes there are changes, and cirrus clouds are also there is ample changes in the last 2 decades. And tropospheric stratospheric cooling, we have seen the mesospheric cooling also from the one of the slides I mentioned. And of course, I didn't mention about thermospheric sinking, but this is one of the important aspects, particularly for the satellite DRACs. So this is the changing scenario in the changing climate. Then what we have seen that we have perfectly utilized our observations to understand some of the process. To conclude my talk, we have filled the biggest gap in understanding the middle atmosphere studies, where the radar was operated from 1993-91 onwards, but the putting of this May and Rayleigh Lidar in 98. So it has given a boom to the middle atmosphere research in India, and we have effectively utilized these May and Rayleigh observations for in situ satellite and re-enhanced dataset validation or comparison studies, and it played a key role in explaining the low latitude mesospheric dynamics, where elsewhere the people are talking about this is related to mesospheric mesopause related aspects, but we could see that this is not related to mesopause, but the temperature inversions happening in the mesospheric altitudes. And these LiDAR observations also helped in assessing the climate impact due to cirrus and utilized aerosols in the changing climate, and played a significant role in the ISRO-NASA Battle 1 campaigns, that is to understand the Asian troposphere aerosol layer properties. And also we have quantified the trend. Quantifying means not just telling that 1 point, see that we have to trend, we have to say at 0.1 degree centigrade increase in a decade. So that is very sensitive. So we could able to, these are because these are high accurate and high resolution measurements. We could able to quantify the change in the temperature right from almost 30 to 80 kilometers by the Rayleigh Lidar observations. And this is going to play important role in understanding the aerosol cloud interaction, in particular the mixed and ice phase. The liquid water we cannot get because the starting altitude is about 8 kilometers onwards, the May Lidar. So we cannot get the liquid water phase, but we will get all the details from mixed and ice phase. And we also plan to use in Stratol 2 campaigns. And of course, by combining the temperatures from the Rayleigh Lidar, and combination of meteor radar, we can get the continuous mesosphere temperatures. And only one thing is lacking is now the trends in the 5 frequency gravity waves in the changing climate. We have not estimated so far. I think Dr. Vishnu Prasad started this work. I think he'll be telling something related, but of course he'll be talking about sodium LiDAR. And the final conclusion is that this LiDAR measurement plays a significant role in mid-atmospheric investigations over Indian region, and it is very helpful to. And actually, there is a limit in the altitude. It cannot go beyond 80-90 kilometers. But there is very much required. The need of the hour is to increase the altitude up to 100 kilometers. Of course, our scientist yesterday, Dr. Raghunath, he has not mentioned about this aspect, but he is trying to put in more telescopes. So he is trying to increase the altitude up to 100 kilometers. And of course, it is very much essential to get such a long-term observations, not only from Gadanki. Of course, my next speaker, Dr. Shon Kumar Sharma, who is the chair of the session, will be talking about some of the related aspects from the mount above, from where that he has obtained. So with this, I'll stop my presentation, and thank you very much again for giving this opportunity to present in front of you.
Okay, thank you, Dr. Ratnam, for a fabulous talk. Really, you have covered the complete spectrum. And now there is because very timely you finished also, thank you. Now there's a time for quick 2-3 questions. So can that I can request the volunteer there, they can take the quick questions from our young scientists or young participants.
Yes. Here.
Hello.
Thank you, sir, for the explanation. Sir, okay. Thank you, sir. Actually, sir, when we are looking to a large scale process, like especially TEJ, LLJ or waves, when we are looking to a single point source, then the intensity spatially is different. So how extent we can represent the data for a large scale process when we are looking to the single?
See, for example, when you're talking about low level jet or tropical jet, this has like a these are all synoptical features. So, for example, that low level jet extends right from like 30 degrees to 120 degrees. So almost like 1,000 kilometers extend. If you have one observation in that 1,000 kilometers, that is enough to get the details. But you do not know about the spatial variation. That's first. Getting the spatial variation, you need to go for the satellite or the re-enhanced data set. But before using them, you have to validate those observations with this, whatever the ground-based instruments. So basically, our ground-based instruments will give the more detailed understanding but the spatial extent that those kind of details will not get from this single instrument. Either the similar instrument should be kept in the satellite to get the spatial thing, or we have to go for the model data analysis. Now, using all these combined different instrument data, now the people are trying to model the atmosphere. But before that, once the model that is ready, that has to be validated again with the observations. So once we know the errors, then we can safely tell that these are the processes happening in the atmosphere.
Okay, thank you, sir. One more, like, sir, you have explained until that higher level aerosols. So, sir, we can say the exactly what are the sources we can separate out, because it's a combine of everything.
So what is happening here? This atoll starts almost like June 15 to September 15. Those 3 months it will be persistently sitting there because of anticyclonic flow, background anticyclonic flow. But what is happening? See, the sources for this atoll is so far we do not know. Even there are the types of the type also we do not know. People thought that it is a sulfate dominated, but using our balloon observers, we could see that nitrate is dominating. And up to that extent we know, and how much it is persisting we know. But what are the sources? What are the types? Those details still we do not know really. So what is happening? This anticyclone, because of anticyclone, anywhere pollution generated, once it reaching to that altitude, once it goes to that anticyclone flow, it is not allowing to go away. So we do not know exactly from where it has come, but it is there.
Okay.
That much only we know.
Okay, sir. And one more, I have seen your paper that
No, that can you please give chance to other, sorry to interrupt, can you give chance to other student to ask the question if anybody want to ask?
Yes, one more person.
Yeah, so that will be good,
Yes,
because
I
you can
will.
discuss with Dr. Ratnam during tea break. I'm sorry
Yes,
to
yes.
interrupt, because other people also should get chance to ask the question.
Yes.
From your last 2 decades observation, you find the significant result in the upward shift in the cirrus clouds. Can you mention the exact reason why it is? Is it due to the convective activities or some?
See, cirrus. Most of the cirrus is through the annuals, convective annuals. So once the convection is there, annuals is there. So in the changing climate, these are all my hypothesis only. Of course, it's not possible to test also. In the changing, in the global warming or changing climate, more convection is expected. More warming means more convection. More convection means more water vapor is being lifted there, and that more annuals what we are expecting. So that will be maybe the one of the reason, but we do not know exactly what is happening. But when we see understand more warming, then more convection, then more amount of cirrus, I mean, even altitude shifting is there, also there. So now even the tropos, if you see, the tropos is not the same earlier. It is tropos goes on increasing. So that increasing is everywhere it is reflected. We cannot pinpoint that one reason for why the altitude is increasing. Yes.
Yes, that I believe that there will be so many questions, because it was fabulous talk covering so many topics from lower atmosphere till middle atmosphere and touching upper atmosphere. So dear all young participants of the workshop, I will request you, don't leave Ratnam. Keep like him like that during tea break and other time also. Whatever questions are coming, please ask. Yeah, he's a very good teacher, so he will definitely satisfy your all the scientific quests. And with this, I will there's a tea break. So,
excuse me, sir.
Yeah.
There is one online participant who raised the hand. My name is Shiva.
Shiva raised hand. Okay. Shiva, can you ask the quick question from Ratnam, please? Sorry, I missed your hand.
Okay, thank you, Samkumar, and thanks, Ratnam. I've been glad to see after 20 years where I left India, all these results. So that is good to see. Just one suggestion and one concluding remark, just basically to see the volcanic eruptions which you have noted is mostly arising from northern hemisphere. But I would like to see whether you could able to address anything southern hemispheric volcanic eruptions, because we have been working on few of them, and it could be interesting to see whether it has passed the continents and also the hemisphere. Maybe we could able to address it via the network. That's my
Yeah, it's it will be very good, very good.
So
I'll be speaking to separately with you, and this is very good. Actually, yesterday only I could able to see that you were able to operate these kind of ladders in South Africa, and it will be very interesting to see that time what happened due to for this eruption. I'll be talking separately with you, Dr. Shivakumar.
Okay. Thank you, Ratnam.
Yes, yes.
Okay, thank you, Siva. Thank you, Ratnam. So now we will take a quick tea break. And so I feel like that 10-minute tea break will be okay, Rudaraman?
Yes, sir. 10 minutes we will break.